Good morning, good afternoon, everybody. Thank you so much for having me for this presentation. So today I will talk about how much POPs has been produced and released into the environment worldwide. So today's presentation will be based on the review paper that my collaborators, like Dr. Knut Breivik here today, and I wrote in 2023. In that paper, we did something that hadn't been done before, to put together the first whole picture view of the global production and release of 25 intentionally produced POPs under the Stockholm Convention. On the left side, you can find the QR code. So in case you would like to access the publication. So in today's talk, I will first give you a broad overview of what we learned from that work. And then I will pick a few key POPs as examples and show their time trend of global release. And I will also compare the trends with environmental monitoring data from the Arctic. And the key point here is that these inventories can help us understand whether the trends we see in the environment in the Arctic are consistent with what we know about global production, use, and release. Okay, so let me first talk about the background of this study. So actually, the story started long, long ago. When I was a child, Dr. Yifan Li from Environment Canada published that very famous paper, the pioneer paper about the global use and emission of pesticide. And you can find a number of astonishing numbers, like thousands or even millions tons of pesticide. And then we had Dr. Knut Breivik, the wonderful work from him about the global use and emissions of PCBs. And the estimate was that historically we produced more than 1.3 million tons of this chemical. And actually, that was 25 years ago. That year, I started my middle school. And when it came to the second decades of the 21st century, PBDE becomes the star props, and Dr. Ganush Abbas and published her great work. And this is about the global stocks and emissions of PBDE. Again, you can see astonishing numbers in the paper. And I was lucky to be part of that work. That was 7 years ago when I was starting my faculty position here at University of Nevada, Reno. And a few years later, my co-supervised student, Dr. Chen Kang Chen, published another paper about the global use and the emissions of chlorinated paraffin, short chain and long chain. And when we look back at these generations by generation efforts to estimate global production and the emission of POPs, I was amazed. So that's why on one day in 2022, I was like, hey, I actually know everybody in these papers. So instead of treating these studies as isolated pieces, why not bring everybody together, and why not bring all the information together into one more complete study? So that's the motivation of the work. So that's why we assembled published data, published estimates of global production and the environmental release of 25 intentionally produced POPs in the history. And for estimates produced by groups outside our team, we took the best available information from the literature. And in many cases, the published studies, the published data were so incomplete. So in many cases, we couldn't have access to the raw data sets. So for these external estimates, we summarized the estimates by decades, such as like 1970 and 1980s. But for estimates produced by our own team, because we already have the high resolution raw data, and in these cases, we put together the information as year-specific numbers, meaning that one estimate for each individual year. By combining these two types of information, we were able to build a data set that is broad enough to cover many pops, but also detailed enough to check long-term time trend. Okay, let's first start with the scale of global production. And you can see on the screen, this is the estimate for each decade across the 25 POPs included in this study. We estimate that about 31.3 million metric tons of pure substances had been produced by humanity as of 2020. And actually, that is a very large number, and it can be hard to interpret because nobody have the idea about this scale. So it make more tangible. So this amount is about 5 times the mass of the Great Pyramid of Giza, or about 3,000 times of the mass of the Eiffel Tower. So you can also see the decade the emission decades by decades had two peaks. The first one is in 2017, sorry, 1970s, and the second one is about 2010s. And maybe we can ask ourselves, are they the same? Actually, they are not the same because the two peaks are dominated by different categories of pops. So before the 1980s, the global production volume was dominated by pesticide pops. For example, we have some names that we are familiar with, like the HCH. So they are dominant in this one. And we also have DDT that is also dominant before the 1980s. But since the 2000, the situation has been changed. So industrial pops like the SCCP becomes the biggest contributor. So you can find that SCCP was the first one, was the largest one for 2000s and 2010s, ranked the first. And if you sum everything together, all the SCCP we produced together, we have produced more than 8 million tons of this chemical. That is crazy. And I'm also showing the whole picture of everything, of all the 25 pops we have. Also, the three HCH isomers, alpha, beta, gamma, are listed as separate chemicals in Stockholm Convention. But if you add these three HCH isomers together, the total is about 8 million tons, almost the same amount of SCCP. So I would say SCCP and HCH are the big two in the pop family. So this is the whole picture of the global production, how much we produced in the environment. And then let's switch to environmental release from production. So if you can still recall, the production curve had two peaks. It's rebounded in the 2000s after declining from the 1970s. But environmental release didn't rebound in the same way. You can just find a single peak. So instead, the emission curve remained at a very low level since the 2000s. So actually, this tells us something very important. Production and the release are not always proportional. But why is that? If you can remember, the second peak in the production is contributed mainly by industry chemicals like SCCP, like PBDE we are talking about. This is because industry chemicals have fundamentally different life cycle patterns than pesticides. I'm comparing the pesticide and the industrial chemicals in this animation. So for pesticide, the pattern is relatively direct. So you produce something and then you use it, you apply the pesticide to soil, to crops, to buildings, and then environmental release take place there. So that's why environmental release is almost intermediate. So basically, you emit or you produce. But the situation is different for industrial chemicals. These chemicals are produced, incorporated into products, stored in stores, in stocks, in-use products, in waste, in a whole bunch of things, and then slowly released into the environment. So this process is through something we call the passive volatilization. So the stocks of in-use products and waste can be treated like long-term reservoirs. So even if the production stop immediately today, emissions may continue for many years because the chemical is still present in the products and the waste. So this difference is very important to keep in mind for us to interpreting the long-term monitoring data. So next, let's look at some specific chemicals, specific examples. One example is DDT. On the left is the collected, this one is the collected global emission estimate. The global annual emission peaks around 1960s and then declined after restrictions and phased out. And for most recent 20 years, when Arctic monitoring data are available, we can see two phases of decline, two stages of decline. The first one is relatively fast, and then the second one was relatively stable. So the important here is that the inventory and the monitoring data, these two, uh, tell us almost a constant story, a consistent story, and that means the global emission estimate do make sense in this case. So the next few slides show additional pesticide POPs like the HCH and chlordane. I just show the trends in their global emissions and the comparisons against the environmental monitoring data. I will not go through every chemical in detail. If you have any questions about them, we can save the questions for our question time. And we don't have an emission estimate for this chemical for most of 20 years. But actually, according to some information and production were still going on during this period. And this chemical has a little bit weird. So we had the first peak contribute by US and the second peak contributed by China. And we do have a lower part between this, but actually from the monitoring data, we couldn't see this gap. Okay, now we come to industrial chemicals. So this is the case of PCB 153. So similar to the case of DDT, for most recent 20 years when Arctic monitoring data are available, we can also see two stages of decline. The first one is relatively slow. The second one is rapid. And actually, if you look at this, we also have a rapid decline at the very beginning and then almost a stable declining rate after that. So actually, the emission estimates and the monitoring data are also consistent. And this is another chemical PBDE 47. And I showed the estimates from high scenario and the low scenario. And because we talk about the in-use stock, the emission from there, and I'm also showing the contribution from in-use stock. Actually, you can find that for the majority of the time, the in-use stock emission make the biggest contribution to the total emission. And the gap is increasing. Actually, the gap is from the emissions from waste stocks. And this is the example for BDE 209. Okay, so we have seen many estimates collected from the literature. So they are generated by something called a forward modeling, which means that we start with production and use data and apply emission factors and estimate emissions over time. So you can find that the generated emission curves are relatively smooth with almost no short-term fluctuations. That's because they are driven by relatively smooth inputs, like the assumed constant emission factors. But this is different from the Arctic monitoring data because we can see the concentration going up and down within the year. And sometimes we also see similar peaks or irregular changes from year to year. So that raises an important question. How do we connect this smooth model-based emission estimate with more available information, more variable patterns we observed in the real environmental data? To address this, we introduce a convolution-based method. So convolution is a mathematical concept. It accounts for the fact that when a chemical is emitted, it doesn't just disappear, it persists. It moves through the air, water, soil, different environmental compartments, and it contributes to the influence of on concentration over time. So instead of assuming that emission in a given year only affects that same year, the convolution-based approach spread the influence of emission across many, many years, a number of years, based on environment persistence. So using this method, we can perform something we call inverse modeling, and we can get something called a top-down estimate. So when I prepare this talk, I ask my PhD student to do some preliminary calculation, quick calculation through rough estimate and rough input data. And what is magical here is that the results are quite consistent with what we collected in 2023 for that paper. For example, for BDE 47, both forward on the left and the reverse on the right modeling indicate that emissions should have peaked around 20 years ago, about 2005, and since then have declined. So the forward modeling shows about 16 times of decline, and the reverse modeling shows that the decline is about 14 times. So they are quite similar. And I'm also including the cases of PCB 153 and DDT to the slides. And you can also find a reasonable agreement between the forward and reverse modeling results, but I will not go through every single detail. Yeah. Okay, so I'm running out of time almost. So let me close with these three main takeaways. The first one, global pop burden has shifted over time. Before the 1980s, the pesticide pops were the dominant. Since 2000, industrial pops have become much, much more important. Second, the pesticide and industrial chemicals have fundamentally different release patterns. Pesticide release often mirror uh, the production and use estimates, but industrial chemicals are more slow and are more delayed. And number three, forward monitoring, for the modeling and the inverse modeling are complementary, and the forward modeling can do something, and reverse modeling can also be used to confirm the forward modeling. So that would be three things we can learn from this study. And thank you very much for your attention. I would be very happy to take any questions you may have.
First, over the last few years, I've been leading the development of an integrated model that I will focus on. But I would like to note that Inga Krogseth, she's been working on the bioaccumulation model, whereas I've been responsible for the physical environment. And then there are a number of collaborators and co-workers who have been involved. So just let me get started with a simple example to explain the concept. So my interest in integrated modeling came about some 15 years ago while I was collaborating with Michael and Frank and Gautier Chou. And we put together the Acumen model and the Cosmopop model into one package called the Cosmoman model. So this is a dynamic and non-spatially resolved model, and it was set up for the Baltic. So here are some research which shows the peak concentrations or the peak emissions or the peak import of PCBs into this region. So I've highlighted four of these curves. So the import curve, you can see it ended about mid-80s, whereas the emissions are delayed. And this is exactly what Lee was talking about, that you have significant delays between production and emissions. Whereas the concentrations in air, they are following closely the shape of the emission curve. However, there is a delay for the trend in human concentrations or human body burdens of about a decade in this example. But what is maybe interesting is to compare containers with each other, and then you get quite a different picture for PCB 180, which is more persistent than PCB 28. So here you can see there are significant time lags between the peak emissions and the peak exposure or human body burdens. And this has potential implications for the interpretation of temporal trends in compartments that react slowly to changes in emissions. For the physical environment, soils and sediments are key, and for the food chain, you have the top predator, the human. But how about spatial variability in temporal trends? And what about the Arctic? So this Cosmo-Man model doesn't answer these questions. So here is the NEM model that we've been working on for the last few years. It's a nested exposure model, we call it. It's a global transport and fate model, and not too different from Better Global, who many of you know, except that it's all built around databases on a half degree by half degree basis. So that's the finest resolution that you can operate the model with. So typically a nested simulation starts with, say, a coarse global simulation for context, and then you zoom into a region of particular interest with finer resolution. As for the compartmentalization, on the right-hand side, there is nothing remarkable about this. It's up to a dozen compartments within a grid cell, so each grid cells contain these compartments. And each of these model compartments are connected via atmospheric flows, oceanic flows, and freshwater flows. And then you have the food chain, which was illustrated on the first slide. But in this drawing, all the transport and fate processes are omitted, and also the link between the organisms, just for simplicity. But just an important note here is that the model for the physical environment accounts for seasonal variability in things like transport and precipitation, wind speed, temperatures, etc., but not from year to year. So the point of departure here for the modeling is on older emission estimates, which is 10 years back in time. So these are the global emissions. And if you operate the physical model, here is an evaluation for 9 EMAP sites in Europe. Zeppelin is at the lower right here. So there are 3 lines showing the model predictions, and then the black crosses are the monthly concentrations from the EBAS database. So in general terms, the model is more fits better with observations that find the resolution, but this is not the topic as such in this presentation. But we were happy to see that overall these differences between measurements and model predictions at the final resolution was comparable to sampling and differences in sampling and analytical methods across laboratories within the EMAP program. So air is among the exposure relevant media. So now I'll bring this forward to the food chain. Or before I do that, I took an output from the splinter for the alert, which wasn't included in the evaluation I showed you. So the model predictions, which are the red dots, it shows a much more smooth decline than the measurements. And this is because NEM doesn't factor in variation from year to year in meteorology, etc. So that wasn't expected either. But then over to the food chain. And Inger, her first study was comparing temporal trends in herring and cod. And here are the overall results from that study. So you have the black line is the median, and the gray line is the range of the model predictions, and similarly for the measurements. So this was the first evaluation driven by the prediction for the physical environment and then up in the food chains. So that study was published in 2023. Next study was by a PhD student called, or her name is Lovise Skogeng. She has now moved on in her career, but she started to explore the possible impact of climate change. And she added 3 new species to the model, either kittiwake and glaucoskull, as well as blue mussels into NEM. And the processes that are included for these organisms are given here, and they are typical for any organism in the model, that it accounts for dietary intake, water and respiration. You have the various elimination processes, which may differ for males and females, and then seasonal variation in body mass and lipid content, and it factors in and calculates things like growth dilution. But this study targeted the climate change-induced altered dietary composition and lipid dynamics, while simultaneously accounting for the inputs from the physical model. But the study did not include any climate change scenarios for the physical environment as such. And here over to the results, which the 3 graphs in the middle, they show the results for the females, and on the right-hand side, you have the results for the males. And then you have either kittiwake and the gull. So there was a fair agreement, and the model seems to capture the magnitude across these birds. If we put this all together, the most recent evaluation adds up with all other organisms. So you have here along the axis the measured concentrations on a log basis versus the estimated concentrations from the model for all these organisms. So the most recent work has been done with Heli and Inger. They have been working on the polar bear model. So here you can see the results for the temporal trends measured with data from the Norwegian Polar Institute versus the model. So what we are working now towards is to look and factor in how climate change may affect the physical environment by choosing selected variables, notably air temperatures, sea surface temperature, wind speed, and sea ice extent, and then also account for annual and seasonal variation from 2015 in these parameters. I should make a confession here that as we did not have historical data from pre-2015, we assumed the same annual cycle before 2015 in these simulations. So in this model, the climate change kicks off in 2015, which is of course not very realistic, and it has implications for the potential comparison between model predictions and observed trends, of course. So here, these are just tentative results, where here I show the results for atmospheric concentrations. So from 2015, you have the red curve shows the climate change scenarios versus the default climate, which is always like it was in 2015. So it suggests higher concentrations in the air. But we can also look into other compartments and organisms now, and we see a general increase, although slightly. So you should really not trust these numbers, but they may indicate qualitatively in what direction it will take. So it seems to be increase all over. And these results, at least for the physical environment, it mirrors earlier work by Matt McLeod. I think it's Vern Schimmel that did these calculations. So, but what we hope one day is to come up with maps like this. So here we show the relative change in PCB concentrations in polar bear, and to try to start to understand how spatial variability may vary within the Arctic. So to conclude or to summarize, I totally agree with Li that emission inventories are key. It's very important, not only for PCB 153, but also many other long-lived POPs, in order to understand POP exposure over longer time scales and larger areas, even under climate change scenarios. But still, the changes in primary emissions are probably much more important because these vary over orders of magnitude from this century. But in terms of comparing air concentrations and emission trends, there are good arguments in these results that these two follow each other closely, and I think that it's common knowledge within this community. However, for compartments that respond slowly to changes in emissions in the physical environment and higher trophic levels, there could be differences in the emission time trends versus the slowly responding compartments. And this is an argument for maybe using integrated modeling of this kind to see what goes on in terms of temporal trends at higher trophic levels. And then just, I think also key is that to go through this rather time-consuming model evaluation exercises is critical for building confidence in model predictions of this kind, because you have, of course, error propagation through these calculations. So there is quite a bit of things to consider. So I'll stop. Thank you for listening.